10, then we'll go to 9. Okay, in 9, we talked about effective mass, and we finished one example about discrete mass system. Okay, and then I started talking about distributed mass parameters and what are the nature of vibration of distributed mass parameter systems. Okay, and then we, in order to get them a mass effective at a specified point, we have to know, the deflection shape of the vibration. So in distributed mass parameter system, there are modes. So here we are doing the approximation of the first mode. Okay, example 9 is determine the effective of the mass. Determine the effect of the mass of the spring on the natural frequency of the system shown below. So the mass here is not 0. This has a spring mass, ms, and we'll assume that the mass is uniform. So it is uniformly distributed. Like the coil diameter is the same throughout, of the same wire of the same diameter. This is uniform. And introducing coordinate y, which goes along the length of the spring from 0 here to L. This is L. So when we know that the x displacement is 0, the spring displacement is 0 here, and the spring displacement is equal to x. Those are the boundary conditions. Okay, so the boundary condition will be that x is at y equal to 0 is 0, and that at L it is equal to x. And then you can assume the variation of the displacement is linear. So you can assume that the spring displacement at any point, at any value of y, is equal to a linear relationship, which is x times y over L. This satisfies boundary conditions. When y is 0, is xs is 0, and when y equal to L, xx equal to x. And you can differentiate to get the velocity. Okay, so the velocity of the spring is equal to dx by dt, which is equal to, y is not function of time. Y is length. X is function of time, which is the motion of the mass. So that will take the derivative only. So it is x dot y over L. Okay, so this is the assumption. We will assume the velocity of the spring element located distance y from the fixed end to vary linearly with y as follows. This is the Rayleigh method. Now you can assume another thing. Okay, but that should be justified. So this is what we think, that the spring velocity is changing linearly from 0 to x dot. And this is the Rayleigh method, is to assume shape deflection. This is called shape deflection. It's something maybe mentioned above here. Okay, so a knowledge of the distribution of vibration amplitude becomes necessary before the kinetic energy can be calculated. Okay, so that is the main thing here. Rayleigh showed that with a reasonable assumptions that at least satisfy boundary condition for the shape of the vibration amplitude. Okay, so we assume something, we assume a function, and that is what we did. It is sometimes called shape deflection. it is possible to take into account previously ignored masses and arrive at a better estimate for the fundamental frequency. The fundamental, as I told you, for continuous systems, we have more than one natural frequency. You have infinite number of degrees of freedom, and accordingly, we will have infinite number of natural frequencies. So omega 1, as I mentioned last time, is less than omega 2. Omega 2 greater than omega 1, omega 3 greater than omega 2, and so on. And this is called fundamental. The smallest is called fundamental. Okay, that is the smallest. So with this, we are assuming to find the deflection, the natural frequency, the fundamental natural frequency. Okay, the next thing is to calculate the kinetic energy, as we did before. You know, we talked about the Rayleigh method is to get M effective from kinetic energy. Okay, so what is the kinetic energy? The kinetic energy for a particle is half m v squared. So for the mass, this is equal to 1/2 m x dot squared. This is for the mass. But for the spring, we will divide, or take a kinetic energy of a point mass on the spring and then do the summation or do the integration. Okay, what is the mass we will take? We take mass of the element is at y, and this will be the mass of elements. Like we take a small portion of the spring of a height or of a length equal to dy, and dy is very small, it goes to 0. So this becomes a point mass. Okay, so we have mass of the element on the spring for a uniform spring is me equal to ms over L times dy. ms is the mass, is in kilogram. You divide by the whole length because this is uniform spring. Okay, somewhere maybe I should write this. Okay, then we can divide ms over L, multiply by dy, and dy goes to 0. This means a point. And you are getting the mass of a point. The kinetic energy for the element will be 1/2 me vs at y squared without it. Okay, vs at L at y squared. The velocity is function of y, and that is the variable changing with length. Okay, but if you want the total kinetic energy of the spring, we have to do the integration of this part. If you substitute, we have 1/2 me, as mentioned, is ms over L times dy times the velocity square. Velocity square is x dot y over L squared. And to get the total kinetic energy of the spring, it is called here the added kinetic energy to this. This is the kinetic energy of the mass, and to add the kinetic energy of the spring. So this is the kinetic energy of the spring. So when you substitute in the integration, it is, you can take 1/2 outside, and then integration from 0 to L. You want to count all the points on the spring. So this is integration from 0 to L of x dot y over L, which is, this is the velocity squared, ms over L times dy. This is the mass. So it is half m v squared. Now, to carry out the integration, there is only dy here. That is the variable, integration over y. Anything that is not function of y, we take it outside. the integration. So this will be 1 over 2. You can take x dot square outside, L squared, right? And L becomes L to power 3 divided by L to power 3. MS, we take MS outside. Then becomes integration from 0 to L of y squared dy. Okay, so 1 over 2 x dot squared over L to power 3 ms, and integration of y square is y to power 3 over 3 from 0 to L. And then when you substitute, you can see this is y to power 3 becomes L to power 3, cancel with L to power 3. Okay, so it is 1 over 2 x dot squared ms L to power 3 over 3, and this is over L to power 3. So L to power 3 cancel out. And then the final answer is 1 over 2. As I told you, you have to keep the factor half and x dot square. So we are finding an equivalent mass or effective mass at y equal to L at x dot. So you need to keep the form of the kinetic energy, because the mass, you want the mass to be added to the m. So this will be 1 over 2, and the common factor is x dot square, and the result of integration is ms over 3. So that is the mass to be added to m. So the system becomes the equivalent system to this. This is with mass, and here is without, with neglecting the mass of the spring. This is K, and the spring is assumed massless here. This is the equivalent for the model. And this mass is m plus the added mass, which is called m effective. What is m effective? When you add the total energy, total kinetic energy will be 1 over 2 m x dot square for the mass plus 1 over 2 ms over 3 x dot squared. So you can take 1 over 2 common, and this becomes the mass plus ms over 3 x dot squared. So this is the m effective equal to, this equal to 1 over 2 m effective x dot squared. So m effective is m plus ms over 3. So the mass is for the equivalent system, m effective is, instead of m only, we have m plus ms over 3. This is the contribution of the mass of the spring with to be added to the mass, which is ms over 3. And once you reach to the model of massless spring and mass that carries a mass m, then kinetic energy is square root of k over m effective. Okay, the spring stiffness is the same. That's not changing. It doesn't change if it is massless or mass or with a mass. So the part to be added, or the mass to be added of the spring, is only third of the mass of the spring. You don't add the total mass, because part of, one point is 0 velocity, the other point, the other end is with x dot square. So the velocity range, there is a velocity range, not the same. It is the spring is fixed at one point and moving with x dot at the other point. Then the kinetic energy will not be just half ms x dot squared. It should be done this in this way in order to get the better estimate of the nature frequency. Okay, so it is when there is mass, you add a third of the mass of the spring. So this is the more corrected equation. So from now on, whenever you have a spring is given with mass, you should use this equation. If the mass of the spring is neglected, then you can use the previous equation of omega n. The model is the same, but we are only showing that the mass, how to calculate the mass of add the contribution of the mass of the spring to the initial frequency. But this is our model. The spring mass, massless spring with M. So we are finding an equivalent system to the original system when at x at the location of the attached mass. Okay, so this is the correct equation when if the spring mass is not neglected. The example 10, an assembly supported beam of total mass MB has a concentrated mass M at midspan. Determine the effective mass of the system at midspan and find its fundamental frequency. Okay, the assembly supported beam under concentrated load at midspan will deflect, and you can find a deflection under concentrated mass as you did in mechanics of material. So for the vibration, this is a continuous system. Okay, this is a simply supported beam. This is the first mode, and this is called with omega 1, and this is the fundamental frequency. This is the second mode and will vibrate with omega 2, and this is the second natural frequency, and omega 2 greater than omega 1, and so on. So the higher modes, the higher is the frequency. So what we will do is to approximate the fundamental mode, which will deflect as shown here. All the material of the beam will go downward and upward of the, below or above, below and above the equilibrium line. Okay, the equation for deflection, or what is the deflection? Okay, the question is to find its fundamental frequency. The fundamental frequency, since there is mass, we have to include the mass to the first mode. This means first mode. And the deflection at vibration is to be assumed. The one used is the deflection of a simply supported beam under concentrated load. Okay, so you have a simply supported beam under concentrated load at midspan with force, let's say P at L/2. This will take a deflection shape, right? This deflection is function of, let's say, X. We introduce a parameter along the length of the beam, which is X, and at X there is the location, the deflection Y. So Y is function of X. Y is changing, of course, along the beam, and its maximum for this case occurs at midspan. So here is Y maximum. Y is 0 here. At X equal to 0, Y is 0. And Y at L, when X equal to L, it is also 0. And you can find using the deflection d square Y by dx squared equal to, what is the equation? M over EI, right? The beam has elasticity and moment of inertia, and the length L from here to here, from end to end is L. And you can find the deflection from this equation. Okay, I'm not going to do the integration now, it will take time, but let me search for it for a minute. um, this cantilever beam. Okay. Okay, I'm not finding that quickly, so I will go back to this. Okay, so when you do the integration, you will get y dy by dt, dy by dx equal to, the moment is, you need to take a section here. Okay, this will be p over 2, right? And this is x. Then this will be minus, this will be plus, right? Px, p over 2, pi over 2, ex, and then you do the integration. This will be px square over, you can take p over 2 ei outside. This will be x square over 2 plus c1. And then you do the integration again. This will be p over 2 ei x to power 3 over 6 plus c1x plus c2. We have the boundary conditions will be at x equal to 0, y equal to 0, and at x equal to L over 2, dy by dx is 0 for this case. You know, this is the, we know that this is maximum. So this will be C1 is 0. Okay. And when we have, no, this is when we can use this condition. This will be at x equal to L over 2. Then this will be 0 equal to P over 2 EI times L square over 8 plus C1 equal to 0. So C1 equal to minus L square over 8. Okay, and the same thing you will do here at y equal to 0, C2 is 0. Okay, so what you will find at the end, y equal to t over 2 ei x to power 3 over 6 minus L squared x over 8. Okay. So you can, this will be, when you add this together, this will be P over 2 times EI, and this will be 8 x cubed minus 6 L square x over 48. Okay, so this will be, you can take 48 outside, P over 48 EI, and this 2, and this becomes 4, and this becomes a 3. So this will be 4x to the power 3 minus 3 L square x. Okay, one more step we will do is take L to the power 3 common. This will be P L to the power cube over 48 EI, and this will be 4x over L to the power 3 minus 3 x over L. Okay, so you can see this is the deflection of the beam. Okay, but what we need is, of course, not this this is the equation for deflection under concentrated load. But what we need from this equation, we will assume that the deflection shape will take this shape. You know, the deflection of the beam will take this shape under first mode. This is the assumption. Which one is that determines the shape is the function of x? This is what we need. Okay, and the whole thing is to be modeled as a spring mass system. This is K equivalent, and this is the M effective moving with Y maximum. So the whole beam, all the points on the beam to be what we did to find the equivalent system at x equal to L over 2, which is in terms of Y maximum. Okay, so the whole system has to be approximated as a spring mass model system moving with Y maximum, not any Y. This is Y, okay, this is Y, but for all values of X, okay? So you need to take the shape function, this is the shape function required, not the whole equation, the shape function. So therefore, we'll assume that Y is equal to Y maximum times f of x, which is 4 times x over L to the power 3 minus 3 x over L. So when this should satisfy the boundary conditions that when x equal to 0, y is 0, right? And when x equal to L over 2, this should equal to y maximum. And we can see if it is not equal to y maximum, maybe there is a factor of half here. Okay, so at y at 0, this is, let me just make y at L over 2, this will equal to y maximum times 4, and this is 1 over 8 minus 3, 1 over 2. Okay, so this will be 4 over 8 is 1 over 2, and minus 3, this becomes, this will be y maximum 1 over 2 minus 3 over 2, and when we subtract, we get minus 2 over 2 becomes minus 1. So it means there is a minus here, okay, because downward we will take it positive. Therefore, the final equation, y will equal to y maximum there is minus or plus minus, right? Yeah. I get a minus. Maybe the equation, yeah, there is a minus. Okay, so that is y equal to y maximum, and this will give me equal to y maximum minus 1. So the factor I want is a minus, which means switching the order of the terms. Okay, so this will be 3x over L minus 4x over L to power 3. So now this will satisfy the boundary conditions. Already y at 0 is 0. So boundary conditions now are satisfied. So this is the equation that we will use. That is the shape function. So at any value or at any point on the beam, it will be related to y maximum. It's like the dependent equation. And the same thing we did for the spring. The spring has a velocity equal to, or x equal to x of the spring equal to x times y over L. So they are related to x. Okay, and the velocity is x dot y over L. So the velocity of any point on the spring is related to x dot, which is the equivalent system will be at x. The same thing for the beam. The motion of any point on the beam will be related to the point, to the motion of the point at midspan. So this is the equation to be used. This is the first step, or this is the shape function. The next step is to use the kinetic energy, as we mentioned in the beginning of the section, that if you can put the kinetic energy in this form, then you can find the effective mass at the specified point. Okay, so the kinetic energy is obtained. The beam is symmetrical. This equation we found is valid for x greater than or equal to 0, less than or equal to L over 2, and the deflection of the beam is symmetrical. Which means that this is the same for x greater than L over 2, less than or equal to L. Is the same. So the kinetic energy, as we did with the spring, we will take a small element on the beam at x. This is dx, and this is deflection y. So the mass of the beam, and the beam is assumed to be uniform beam with mass mb, and of course it is elastic. Then mass of the element will be mass of the beam divided by L multiplied by dy, multiplied by dx. And then the kinetic energy for the element, as we did with the spring, this will be 1 over 2 mass of the element, the velocity squared. Okay, this is y dot at x squared. And then you substitute for the element, which is 1 over 2, mass of the element is mass of the beam, divided by L times dx. And the velocity, or y dot square, we have y dot. We obtain y dot. That is equal to y maximum 3x over L minus 4x over L. This is f of x only. There is no time here. This is function of time. Y maximum is function of time. So the only term that will be differentiated is y maximum. So this will be, the kinetic energy will be, this is squared, so it is y dot maximum multiplied by the f of x, which is 3x over L minus 4x over L to power 3. This is the whole thing is squared. This is the kinetic energy of the element. The kinetic energy for the beam to be, we have to integrate this from 0 to L multiplied by 2 because it is symmetrical. So this is 2 is the factor, the integration from 0 to L over 2, and then you multiply whole thing by 2. That will give you the total kinetic energy. So 1 over 2, 2 times mb over L, okay, times dx, this is the mass of the beam, times y dot maximum 3x over L minus 4x over L cube, all squared. Okay, you can expand this expression, and anything that is not function of x can be you can take it outside the integration, including y dot maximum, you take it outside. 2 mb over L, we take it outside the integration, and then the only thing to be integrated is 3x over L minus 4x over L to power 3, the whole thing to power 2. And that will give you the integration result. So you keep the factor half, as I told you before, and you keep the coordinate velocity square as a common factor, and then in between them is the mass to be added. Okay, so this is not, yeah, this is the mass to be added. You know, this is T add. Okay, which is equal to the mass to be added is 0.4857 MB, which is almost half of the mass of the beam. Okay, you can say this is almost half of the mass of the beam. So M effective, which is the total mass of the beam and the attached mass on the beam, which is M plus the effective mass, 0.4857. So in the formula sheet, I put this as almost 0.5. So I use 0.5 rather than 0.4857. It is already an approximation. So it is almost 0.5. So what I did in the formula sheet, just to make it easy, I just put this as 0.5 mass of the beam, and I found this also used in some of the references. And this is the model. Okay, and massless beam, massless spring with K equivalent is for a beam is 48 EI, similarly supported beam, over L cube. Okay, which is, you can see this from, you know, this equation. Okay, when you put x equal to L over 2, you will find the relationship between P and Y maximum, and that will give you K. Okay, so K is 48 EI over L cube because this is simply supported beam, and the mass effective is the mass at midspan plus the added mass of the beam. And once you determine the mass effective, omega n is square root of K effective, K over M effective, K equivalent over M effective, okay, which is 48 EI over L cube over M plus 0.4857 MB, okay, the mass of the beam in kilogram. This is the for distributed mass parameter system, 2 examples. In the tutorial, we have 4 questions. Any questions so far? Okay, we have 3 questions in tutorial 4. 3 of them about discrete mass system, parameter system, and the question 4 is about a cantilever beam. Okay, so the remaining time, let me just go through this quickly. Shown below is a cantilever mechanism. It is used to convert the rotary motion of a shaft into oscillating or reciprocating motion of a valve. The follower system consists of a push rod of mass MP, a rocker arm of mass MR, and a mass moment of inertia JR about its center of gravity, a valve of mass MV, and a valve spring of mass MS, and stiffness K. Find the equivalent mass effective, okay, of this cantilever system at point A and the natural frequency. So point A is this point, This is the cam, and this is not part of the system. The cam is not part of the mechanism. That is oscillating. This is in rotation, not related to vibration, as related to the natural frequency, I mean. So the system consists of the follower that has a mass. This is assumed rigid. Those all are rigid except the spring. The push rod is moving, is connected with the rocker arm. The rocker arm is the rigid link, and connecting the push rod, this one, and the valve and the spring as well. Okay, those are the push rod and the valve are assumed rigid. The rocker arm is also rigid, and point A and point B motions are related, which is XA and XB are related. Here, XA is called X, and it is equal to XP, which means the motion of the push rod, and point B is called XV, which means the motion of the valve. The equivalent to this is, this is like a rocker arm pivoted here, and it carries a mass MB and a mass MV, which is for the valve, plus the mass of the spring. Okay, what is the mass of the spring to be added to mass of the valve? Is what we did an example for the spring mass system. So this is MV plus M of the spring divided by 3. We don't have to do the integration again. Okay, so this is the system with the spring here. And this to be defined as an equivalent system to this is a spring and M effective moving with X and X equal to XP. And this is K effective as well, because that the spring is not at the same location of point A. So we have to find the K effective. And this mass is, this spring is massless for the model. Okay, this is the model. From here, once we reach to this model, omega n is square root of K effective divided by M effective. To get the K effective, to get M effective, we use kinetic energy. This is a point mass. The rod is a point mass. Its kinetic energy is 1/2 MP XP dot squared. And the valve also has a kinetic energy. This is fixed here. This is the engine block, which is fixed. And the kinetic energy for the valve is half mv xv dot squared. And the kinetic energy for the spring is 1/2. We did this before in the example, is 1/3. 1/2 ms/3 xv dot squared, because the spring is moving with the same motion of the valve. Okay, and the rocker arm it is rotating about O, so its kinetic energy is 1/2 JO theta dot squared. Now JO is not given in the question. JR, which is about CG, is given, and the location, and MR, which is mass of the rocker arm, is given, and its location is L3. So JO is obtained by using parallax theorem, which is JR plus MR times L3 squared. This is JO, theta dot squared. So those are all the kinetic energies in the system. Of course, the cam is not part of the oscillatory system, so we don't include that. And the spring is fixed here, and it is moving with the other end with the valve. And this is why its kinetic energy is half ms over 3 x dot v squared. The mass is not zero for the spring, so we have to include its kinetic energy. So what you can do is to get the kinetic energy, you add all the kinetic energies. So T equal to 1 over 2 mp x p dot squared and so on. So the kinetic energies is the summation. So the other thing we need to find is the relationship between the motions x and x, v and theta. And I think we did this in one of the examples. Here. Okay, this one. So this is the relationship you can, as we did, I think we did it here. Yeah. Okay, that is A equal to sine theta, and we approximate this as A theta and B theta, and all the relations are just similar. Huh? You can find the relationship. You go back to that example. And then you make everything in terms of X. And then you find the potential energy. This is the kinetic energy. Then you find the potential energy. And the potential energy is only comes from the strain energy of the spring, which is half K xv squared, because the spring is moving with xv. So what you need to do is replace xv in terms of x. And I think you can do that. In question 2, we have the mass. This is a rocker arm. This is a rack, and here is 2 gears in mesh. So the rock is moving with x, and let's say this is moving with theta 2, and this is moving with theta 1. Okay, or theta, yeah, theta 1, theta 3. There is no theta 1. X, theta 2, theta 3. Theta 2 and theta 3 are related, and also x and theta 2 are related. The question is to find M effective in terms of x and K effective in terms of x. It means to find an equivalent system. This is massless, so there is no mass here. This is a torsional shaft. This is a shaft, so it is providing a torsional stiffness. You can take its moment of inertia is 0 for the shaft. It's only providing KT or K3. KT equal to K3 here, as mentioned. Just used KT equal to K3. So the question is to find an equivalent spring mass system with M effective, okay, and K effective at X. Okay, and once you reach to this model, omega n is equal to the square root of K effective over M effective. Okay, try to solve, complete the solution. The same thing here. We have a rigid link, and this is an arm, rigid arm. And the question is to find equivalent system in terms of X. The springs, here I add a mass for the spring, ms1, and here also has a mass ms2. And this JO this is point O given. There is no need for using parallaxis theorem because JO is given directly. And at the pivot, we have KT as well is given. Okay, you find the relationship. You can call this as x1 is moving with x1. This is moving with x2, and x equal to x2. And then you can find where you need the kinetic energy and you need the potential energy in terms of x, so that you get an equivalent spring mass system at x. For the cantilever beam, you can follow the example we did for the simply supported beam. What you need is the deflection shape of there is a factor here you need to find, and f of x only. Okay, in terms of y maximum. This will deflect under concentrated load P, and this is y maximum. So what you need is y maximum times f of x, and maybe there is a factor half here, so I just will make it equal to c. As we did in the example for the simply supported beam, the factor was -1. Okay, here you need to find the factor, maybe it is half. And then you can find the added mass. This is the added mass. Okay, so write the equation of its fundamental frequency. This is the mass. The net frequency would be square root of k over m. Okay, any questions? Okay, so have a nice weekend. Next week we will start, for those who are going to come to the university, we will start maybe on Sunday. I will send you a message to confirm you if you can come and to which room. Okay, I prefer to use rooms in 14 near to my office, 14106.
بيكون لسجل